Hi, folks. Announcements first. I'm gonna get the unpleasant one, at least for me, out of the way. I was informed of an integrity issue on the last exam. I have the names of the individuals, but I would rather you tell me rather than, because I'm more likely to go a little easier than if I have to go with what Rebecca told me. Specifically, I was told about tilting a page for naming towards their neighbor. And I was given the names of the individuals. So please, if you were the responsible party, please come talk to me. I'd rather hear it from you. Otherwise, you will know when I get the test graded, because I will be making a note of it on your exam. I will say that was an extreme disappointment. I didn't expect it from this class. I have a lot of confidence in this class. I thought highly of the individuals in this class. And to hear that just was very disheartening. So, again, I would rather you than just strictly go with what she told me. That being said, I will be in my office today from 2:40 to 4:30. 2:40 to 4:30. Come see me. We'll have a conversation. Okay. Now that I've gotten the piece of information that I did not want to discuss out of the way, let's discuss this upcoming week. Number one, today I will be doing stoichiometry. We will be doing stoichiometry with Avogadro's number, molar mass, mole-to-mole ratios, balanced chemical equations, and so on and so forth. My goal is to get into limiting reactants and theoretical yield and percent yield. Tomorrow, we will be doing the titrations lab. Titrations involve solutions, which means I will need to introduce the concept of molarity and discuss solution stoichiometry. So come prepared for the first hour to take notes. Then you'll be able to get into the titration itself. Thursday, if all goes well on Tuesday, today and Wednesday, then Thursday I will start talking about electrolytes, solubility rules, strong acids, strong bases, weak bases, and get into information that is directly related to the lab we did prior to spring break. As far as there is no homework due today. There is no quiz on Thursday. The only thing going on is this Thursday, for those that signed up for the STEAM night. This Thursday is the STEAM night at Conway High School in the Buzz Bolden Arena. I would expect you to get there right at 5. That way I can demonstrate the activity that you will be doing. And we will be done by 7:30. Basically, I usually start shutting down a little early. So we will be done by 7:30. I will have all the supplies for you. That is my goal over the next little bit of time today, is to get all the supplies together. Any questions so far? I think that covers this week. The last thing I want to say is, obviously I'm not passing that test today, otherwise there would be a stack up here. I didn't get them until yesterday. The withdrawal deadline, whether you want to withdraw from my class or another class, is Monday of next week. If you are trying to determine whether or not you should withdraw from my class and need to know where you stand, you can come see me this week, and I will grade your lab, get it graded so that you can know where you stand. I mean, not lab, test. I'll grade your test and be able to tell you where you stand. Keep in mind that one bad test grade is not the end of the world, because I do drop your lowest test. It may mean that you were taking the final, but I do drop your lowest test grade. I believe it's 2 quizzes and 2 homeworks and 1 lab. So there's lots of things I'm dropping. So I can give you a better idea of where you stand once I go through, and because I already have it, I have a column where it does all the drops for me. I just don't show you that column because it's confusing to most people. So I'd rather you come see me and me discuss that column with you individually. questions for me. Okay, then we're going to get into conversions today. I introduced the concept of stoichiometry. Basically, stoichiometry is chemical conversions. I introduced it on Tuesday prior to spring break, and one of the last things I did is develop this table for you. These are the conversion factors that at this point, until we talk about molarity, that you have been introduced to. The first is Avogadro's number. Avogadro's number is going to be the conversion factor you will use anytime you see the word atoms, ions, or molecules. Or it will be, I should say, one of the conversion factors you will need if you see the words atoms, ions, or molecules. The second conversion factor is the molar mass. The molar mass we discussed prior to spring break, and it is grams of whatever is equal to moles, is equal to 1 mole of that substance. You will use the molar mass as a conversion factor if you are dealing with grams at any point in the problem. The last one is the mole to mole ratio, and there are actually 2 locations where you can find the mole to mole ratio, and it is directly dependent upon what the conversion is. The first location for the mole to mole ratio can be found in the chemical formula. Specifically, it's the subscripts associated with the chemical formula. This particular conversion factor is valid if you are dealing with needing to go between an element in a compound and that compound. But the second place we could get the mole to mole ratio is going to be from the balanced chemical reaction, where we actually get the coefficients. And the coefficients describe the number of moles of each substance in that balanced chemical reaction. You will wind up using this variation of the mole to mole ratio if you're converting between 2 substances in a balanced chemical equation. So what we're going to do is we're going to look at examples, and that is going to be the biggest thing we will be doing today is examples. So let's just go with a question. How many oxygen atoms are in 29.75 grams of potassium dichromate? As with any dimensional analysis, you identify what you have been given. We have been given 29.75 grams of potassium dichromate. You identify what you want to solve for. We want to solve for oxygen atoms. Now, we're going to start breaking this down to determine what conversion factors we will need. The first thing I do is I look at the formula, even though my iPad wants to change it. I look at the formula and I realize there are two different formulas here. Because there are two unique formulas, I am going to need a mole to mole ratio. Because I am talking about an element within a compound, the mole to mole ratio is going to come from the chemical formula. According to the chemical formula, there are 7 moles of oxygen to 1 mole of K2CR2O7. The next thing I look at is I look at the unit of the starting material and I see grams. Grams tells me I'm going to need the molar mass. Because anytime I see grams, I'm going to need molar mass. So I figure out the molar mass. I have 2 potassiums at 39.10. I have 2 chromiums at 52.00. And I have 7 oxygens at 16.00. Those numbers coming from the periodic table. So the potassium contributes 78.20 to the overall mass. The chromiums contribute 104.0 to the overall mass. And the oxygens contribute 112 to the overall mass. So therefore, that's 294.2. That is actually 294.2 grams of K2CR2O7 is equal to 1 mole of K2CR2O7. The last thing I see is I see atoms. Atoms tells me I'm going to need Avogadro's number. So it is going to be 6.022 times 10 to the 23rd oxygen atoms is equal to 1 mole of oxygen, because 6.022 times 10 to the 23rd of anything is equal to 1 mole of that thing. Take a moment. And yes, I used colors to help highlight what I wanted to do. Take a moment and look at where I got the conversion factors based off of that table that I started with. And ask questions. Okay. No questions. Then we begin the math. You start your math with what you were given, which is 29.75 grams. K2 CR207. Our first conversion factor needs to have K2 CR207 grams in it. So we're going to be using the molar mass. Of the molar mass, the 294.2 grams of K2 CR207 go in the denominator, with the 1 mole in the numerator. The grams had to go in the denominator so that the unit and the substance canceled out. Now we're left with moles of K2CR207. So our next conversion factor is going to have moles of K2CR207. So we're going to use the mole to mole ratio, which 7 moles of oxygen is 1 mole of K2CR207. The mole of K2CR207 went in the denominator so that the unit and the substance will cancel out. Notice I keep saying unit and substance have to cancel. But I didn't want moles of oxygen. I wanted atoms of oxygen. So I'm going to use Avogadro's number, which is 6.022 times 10 to the 23rd. Oxygen atoms is equal to 1 mole of oxygen. The mole of oxygen was placed in the denominator so that the unit and the substance would cancel out, leaving oxygen atoms. Now to do the math. And when you key this into the calculator, you will get 4.263 times 10 to the 23rd oxygen atoms. Yes.
You're just using that original 29.75 grams.
Okay. Actually, I used everything. So I was asked about sig figs. In my original value, there were 4 significant digits. In the molar mass, the mass had 4 significant digits, while the mole portion is an exact quantity, so it has an unlimited number of significant digits. Mole to mole ratios are exact quantities, so they have unlimited number of significant digits. And then the Avogadro's number, there are 4 significant digits in the mantissa of the number, and the mole is an exact quantity. So when you look at this, the measurement with the fewest had 4 significant digits, so my answer needed 4 significant digits. Folks, setting up the problem with, and here's where I'm going to get I will get very tricky. Setting up the problem with units and formula will give you about 75 to 80% of the points. So in other words, if you key it into the calculator incorrectly, you're not going to lose all the points. If you don't, and I don't pay attention to significant digits at this point, except in lab. Usually, it is 1 point for the number and 1 point for the unit. So in other words, when I look at it, it's 2 points for the answer. 1 point for the number and 1 point for the correct unit. Now, the Tuesday prior to spring break, or the Thursday prior to that, you got this flow chart. If you don't like that table I gave you, you can use this flow chart. We started with grams of potassium dichromate, and we ended with atoms of oxygen. So we started here and ended here. On the arrows, it tells you what the conversion factor should be. So the first conversion factor should be the molar mass. The second conversion factor should be a mole to mole ratio. The third conversion factor should be Avogadro's number. So if this is the best way for you to get it down, that's fine. Now, the only problem with this is what I'm doing here is something that's going to carry through to College Chem 2. It's going to carry through to Organic 1, Organic 2. You're going to see this again. So it's better to know which conversion factors you need based off of what you are given and what you want to solve for than to memorize this. But this can help you until you get it down. Any questions? Let's look at another problem. That was supposed to be sulfite, not sulfate. Okay. Aluminum sulfite reacts with sodium hydroxide as shown in the reaction, where aluminum sulfite plus 6 sodium hydroxides makes 3 sodium sulfite and 2 aluminum hydroxides. How many grams of aluminum hydroxide are produced from 5 grams of aluminum sulfite? Okay. We identify what we were given. We were given 5.0 grams of aluminum sulfite, which is Al2SO3. We identify what we want to solve for. We want grams of aluminum hydroxide, which is AlOH3. Now we break it down. First thing I note is aluminum sulfite and aluminum hydroxide are unique formulas. Therefore, we are going to need a mole to mole ratio, which is going to come from the balanced chemical equation. According to the balanced chemical equation, 1 mole of aluminum sulfite produces 2 moles of aluminum hydroxide. Those are coming from the coefficients of the balanced chemical equation. The next thing I note is I have grams of aluminum sulfite. Anytime I have grams, that means I'm going to need the molar mass. So according to this formula, there are 2 aluminums, 3 sulfurs, and 9 oxygens. Aluminum is 26.98. Sulfur is 32.06. And oxygen is 16.00. The aluminum, therefore, contributes 53.96 to the overall mass. The sulfurs contribute 96.18, and the oxygens contribute 144.0. So we have a molar mass, when we add it together, 294.14. So that means that there are 294.14 grams of Al2SO3. 3 is 1 mole of Al2SO3. 3. Continuing this process, the next thing I notice is that I have grams of aluminum hydroxide. Again, grams means molar mass. I have 1 aluminum, 3 oxygens, and 3 hydrogens. Aluminum is 26.98. Oxygen is 16.00, and hydrogen is 1.008. So the aluminum contributes 26.98. The oxygens, 48. And the hydrogens, 3.024. Meaning that aluminum hydroxide has a mass of 78.004. So that is 78.004 grams of ALOH3 is equal to 1 mole of ALOH3. Now that I have my conversion factors, I'm ready to do this math. Starting with what I was given, which is 5 grams of Al2SO33. My first conversion factor must have grams of Al2SO33, so therefore I'm going to be using the molar mass. Of the molar mass for that, I am going to put the mass portion in the denominator. And the mole portion in the numerator. The mass portion was placed in the denominator so that the unit and the substance canceled out. Now I'm left with moles of aluminum sulfite. At this point, I'm going to use the mole-to-mole ratio of aluminum sulfite to aluminum hydroxide. According to the balanced chemical equation, 1 mole of aluminum sulfite produced 2 moles of aluminum hydroxide. The aluminum sulfite in the mole-to-mole ratio was placed in the denominator so that the unit and the substance would cancel, leaving aluminum hydroxide in the numerator. But you were specifically asked for grams of aluminum hydroxide, not moles. So we use the molar mass of aluminum hydroxide to get it into grams. Of the molar mass, the mole portion is placed in the denominator so that the unit and the substance will cancel out, leaving grams of aluminum hydroxide. Now that you have what you need as far as unit and substance, you are ready to do the math. And when you complete this math, you get a value of, 2.7 grams of aluminum hydroxide. Folks, this math is not just math. It has a meaning behind the math. That's one of the reasons I like chemistry. I have a degree in chemistry and a degree in mathematics. The reason I like chemistry better is because it's applied mathematics. This has a meaning. This literally means that the maximum or theoretical yield of aluminum hydroxide that can be made from 5.0 grams aluminum sulfite in this reaction is 2.7 grams. This assumes that every particle of aluminum sulfite behaves according to this reaction. It assumes perfection. It assumes that there's no side reactions. It assumes a lot of things. It assumes absolute perfection. So this math has a meaning. It's not just a math problem. It has a meaning. In so doing, I have introduced a new term. Theoretical yield. Basically, this is, in theory, how much can be produced. In theory, how much can be produced. So when we perform these mathematical problems, again, we're assuming perfection. We're assuming no side reactions. We're assuming perfect behavior. We're also assuming we can get everything out that we put in. So, one term that you need to be familiar with is theoretical yield. It is the maximum quantity of material that can be retrieved assuming the reaction behaves perfectly. Okay. In our time in the laboratory, We have had a couple of reactions where we started with a specific quantity of one reactant and we had extra of the other. An example would be when you took the copper mesh and placed it in the crucible. And then you heated that crucible and that copper mesh changed colors. That copper mesh was reacting with oxygen in the air. The oxygen was in excess. Another time was, I was trying to think of copper sulfate. Well, those would have been the same. But that is an example where you had multiple substances but you had one reactant that was the limiting reactant. So an example of what I just talked about was the copper mesh plus oxygen going to form copper monoxide or copper oxide, copper 2 oxide. Where you started out with copper mesh as a solid, oxygen gas, and you made copper 2 oxide solid. In this case, you had oxygen in excess because, I mean, the oxygen was drawn from the atmosphere. In this case, the copper would have been the limiting reactant in this problem because, again, oxygen was in excess. A limiting reactant or limiting reagent, or how, I mean, basically is going to be one, the reactant that is completely used up. And two, it is going to be the reactant that determines the theoretical yield of the product. It's real easy to identify the limiting reactant when you have something like copper reacting with oxygen in the air. It's easy to identify who's going to run out first. But there were other reactions that you did. For example, you took
trying to remember what you took. PB N032, I believe it was. Aqueous. And you reacted that with 2 potassium iodide aqueous. And you got out PbI2 solid and 2 KNO3 aqueous. If you'll recall in lab, I think you added 10 drops of this one and 10 drops of this one. So, which one was the limiting reactant? They're not both a limiting reactant. We're not going to work that problem. But I wanted to illustrate that in lab, we frequently start out with, I'm going to add this amount of reactant A with this amount of reactant B. And I want to know how much product I can get. So let's talk about how to determine the limiting reactant and theoretical yield if you start or if you add 2 substances together. There are a number of ways to do this math. I'm going to teach you what I find has been the simplest. Step 1, convert reactant A into grams of the desired product. Two, convert reactant B into grams of the same product. The lowest quantity obtained in step 1 and 2 is your theoretical yield. And finally, the theoretical yield came from the limiting reactant. Let's look at this in action. The reaction for the combustion of ethane is 2 ethane plus 7 oxygen goes to form 6 water plus 4 carbon dioxide. 1.45 grams of ethane was burned in 4.5 grams of oxygen. Determine the theoretical yield and limiting reactant. Okay. We're gonna pick, because it didn't tell me who I wanted to go to, we can choose the water or we can choose the carbon dioxide, but we're gonna pick one of the products. I'm gonna pick water as the product I'm going to convert everything into. So in step 1, I'm going to convert 1.45 grams of C2H6 into grams of water. In step 2, I'm going to convert 4.50 grams of O2 into grams of water. Using the method that we just talked about, I'm going to perform this calculation. Now, I'm not actually going to write everything out, though if you need to, you could. The molar mass for ethane is 30.068 grams of ethane is 1 mole of ethane. According to the balanced chemical equation, 2 moles of ethane react to form 6 moles of water. And then the molar mass of water is 18.016 grams. Doing this math, you get a value of 2.606 grams of water. We do the same thing for the oxygen. We're going to convert the oxygen into water. First thing we need to do is use the molar mass of oxygen to get it into moles of oxygen. And then we use the balanced chemical equation, which there are 7 moles of oxygen to 6 moles of water. But ultimately, we're going to get that into its mass. And we find out it is 2.172 grams of water. I'm letting everybody catch up at this point so I can explain the meaning. Okay, folks. The way this is describes, what this math describes is it says, if every bit of the ethane gets used up, we could get out 2.6 grams of water. But if every bit of the oxygen gets used up, we can only get out 2.17 grams of water. So the theoretical yield is 2.172 grams of water, because that is the lowest quantity. Because at that point, there is no more oxygen. The reaction cannot continue any further. Because once one of those reactants is used up, you don't continue, it just ceases. So, oxygen is the limiting reactant. Most common mistake is, well, there's really two things that's a common mistake. Number one, I want you to notice, you can't simply look at this number and figure out who the limiting reactant is going to be. You can't simply look at the starting quantities and know who the limiting reactant is going to be. That is because there are other factors that come into play. Other factors such as the mole ratio. Other factors such as a difference in molar masses. There are other things that come into play. So you cannot look at just the starting quantities and determine who the limiting reactant is. That's mistake number one. Mistake number two. Notice that the theoretical yield is one of these two numbers. It is specifically the one that is in the lowest quantity. Because again, once I make 2.172 grams of water, I have no more oxygen. I cannot continue the reaction without oxygen. So the theoretical yield is whichever one of these is in the lowest quantity. Because that's going to determine who ran out first. I have one more term I want to introduce today. And it's not a hard term, even though people mess up this math all the time. It's actually an easy term. If I asked you, how do you determine your grade on one of my tests, what would you tell me? If I asked you to determine your percent grade on one of my tests, what would you tell me?
Divide what you got by the whole.
Divide what you got by the whole times 100, right? And that would give you your percentage. In other words, your percent is equal to the actual divided by the theoretical
times 100. Folks, when we're talking about a chemistry reaction, the percent yield is the actual yield divided by the theoretical yield times 100. You just up in the math that we've been performing, get to the theoretical yield. Guess where the actual yield comes from? Huh? What you got from the experiment. So when you go into the lab, what you get out of the experiment is your actual yield. And then you calculate the theoretical yield. And that ultimately can give you the percent yield. We will pick up on Thursday with another one of these problems, but we're going to take it a step further and get the percent yield. Thank you.